Welcome to day 6 of our pointers mastery course. Today we move one level deeper, literally, into the world of memory by learning about double pointers or pointers to pointers. These are not just an academic concept, they are widely used in real world scenarios such as dynamic memory management, 2D arrays, and even complex data structures. This session will be hands on, visual, and packed with a mini project that brings double pointers to life. Here's what we aim to accomplish today. We will begin by defining and understanding what double pointers are, what makes them different from regular pointers. Next, we will learn how to use them to dynamically allocate and manage 2D arrays, which is an important use case. We will also visualize how they behave in memory, because this topic is best understood with diagrams and step-by-step tracing. Finally, we will solidify our learning by implementing a real-world matrix multiplication project using everything we cover in this session. So what exactly is a double pointer? In simple terms, is a pointer that stores the address of another pointer. You are not pointing directly to a value like an integer or a float, but rather to another variable that points to that value. Let's look at the syntax. Int star star ptr2. This means that ptr2 is a pointer to an integer. For example, if we have int val assigned 10, then int star p assigned ampersand val, this gives us a pointer to val. Now if we declare int star star pp assigned ampersand p, then pp is a pointer to p. That's two layers of indirection, and that's where double pointers shine in managing complex memory references. Let's unpack this with clarity. The first level, int star p, points to an integer. The second level, int star star pp, points to a pointer to an integer. When we write star pp, we are asking for the value stored at pp, which is p, the pointer to val. When we write star star p, we go to one level further and get the value stored at the location that points to p, which is the actual value of val. So in our case, if val assigned 10, then star star p gives us 10. This layered access forms the foundation for multidimensional arrays and deep data manipulation. Let's visualize how this looks like in memory. Imagine you have three variables, val, p, and pp. Val is at memory location 0x100 and holds the value 10. P is at 0x200 and holds the address 0x100, meaning it points to val. pp is at 0x300 and stores 0x200, the address of p. So when we dereference pp once, star pp gives us 0x100 and star star pp gives the value at 0x100, which is 10. This chain of addresses helps us understand how pointers to pointers can track and manipulate complex memory references. Now the real question, why do we need double pointers? Well, they allow us manage memory dynamically in two dimensions, which regular pointers can't do easily. When you create dynamic 2D arrays, we need to allocate memory row by row, and that's where a pointer to a pointer becomes useful. They are also essential when we want to change a pointer inside a function. If we pass a pointer by value, the function can't change its address, but with a double pointer we can modify the original. They are also foundational in many data structures like linked lists with dynamic nodes, tree structures, and graphs. In short, they give us flexibility and power in memory manipulation. Let's talk about a major application, allocating a 2D array dynamically. In a 2D array, we have rows and columns. We can't just use a simple malloc call. First, we declare a double pointer int star star matrix. Then we allocate memory for rows, matrix assigned malloc rows times size of int star. Now for each row, we allocate columns, matrix I assigned malloc calls times sign of int. This two-step process creates a true 2D structure dynamically where each row is independently allocated. This gives us flexibility but also responsibility to manage memory correctly. Memory management is a two-way street. What we allocate, we must deallocate. To free a dynamically allocated 2D array, first loop through each row and call free matrix I. This deallocates each row's memory. Then call free matrix to deallocate the array of row pointers. Failure to do this results in memory leaks, which can crash programs or consume excessive memory in long-running applications. So make sure you free your memory in a reverse order of allocation. Let's cover some common pitfalls. First, never dereference a pointer before it's initialized. This leads to undefined behavior or segmentation faults. Second, always check the return value of malloc. If it returns null, your program should handle that gracefully. Third, don't forget to free every block of memory you have allocated. And finally, when using star PTR, star PTR, or even star PTR, always ensure your dereferencing levels match the structure of your data. A mismatch in pointer depth can corrupt memory or crash your program. One of the best ways to understand double pointers is by drawing them out. Use boxes to represent variables and arrows for pointers. Track how each pointer connects to another memory location. Track this exercise helps us grasp how indirection works and builds intuition about what each level of star is accessing. It also makes debugging much more easier when you can visualize the memory layout. Now let's get practical. Your task is to dynamically create a 2D matrix using double pointers. You will prompt the user to enter the number of rows and columns, then allocate the matrix dynamically using malloc, take input to fill it, and display the matrix. Finally, free all the memory to avoid leaks. This task reinforces everything we have discussed, from pointer allocation to dereferencing and memory cleanup. Here comes your mini project for day 6, matrix multiplication using double pointers. You will dynamically allocate two input matrices A and B. A should have dimensions m by n and B should have dimensions n by p. Then create a result matrix R with dimensions m by p. Perform multiplication using nested loops, just like in math. Rij assigned Rij plus Aik times Bkj. Make sure to free all memory once done. This project combines your logic skills and pointer knowledge to build something meaningful and scalable. Let's walk through the structure of your code. Start by allocating 3 double pointers A, B, and R. Use loops to take input into A and B. For the core logic, use 3 nested loops, outer for rows of A, middle for columns of B, and inner for computing the dot product. Store the result in Rij. Once completed, print R and free all memory block by block. This not only tests your understanding of double pointers, but also of clean coding practices. To summarize, double pointers are an essential part of working with dynamic data in C. They allow you to create 2D arrays on the fly, change pointers inside functions, and serve as building blocks for dynamic data structures. We explored the syntax, memory behavior, allocation, and deallocation of double pointers. Today's metrics project put theory into practice, showing us just how powerful and flexible this concept really is. Practice is key, so revisit the code, read order diagrams, and experiment. You will now well equipped to use double pointers confidently in real applications. Hello and welcome to day 7 of our pointers mastery course. Today we are going to explore a fundamental concept in C and C++ programming, pointers and strings. These two elements, when combined, give programmers low-level control over text manipulation and data processing. Whether you are building simple command line tools or working on embedded systems, understanding how to handle strings using pointers is a key skill. Let's dive deep into how characters are stored in memory, how pointers traverse and manipulate these strings, and how we can use them to build practical applications. Let's begin by setting the objectives for today's session. First, we want to understand how character arrays, also known as strings, interact with pointers. Second, we will explore how to perform common string operations such as copying, comparing, and calculating the length of strings using only pointers. And finally, we will apply everything we have learned to build a mini project, a word counter, that will reinforce your conceptual understanding through practical coding. By the end of today, you should be confident in using pointers for efficient and elegant string processing. Now let's look at how pointers relate to character arrays. When we assign a character array like str assigned word, we can then point to it using a character pointer such as char star ptr assigned str. This pointer now holds the memory address of the first character, w in this case. Using pointer dereferencing, we can access each character. Star ptr gives us w, star ptr plus 1 gives us o, and so on. This is a powerful technique that allows us to move through a string character by character using pointer arithmetic without relying on array indexing. Traversing strings using pointers is both elegant and efficient. Consider this simple code snippet: char star b assigned str while star p not equals to backslash 0, cout star p p plus plus. What's happening here? We start by pointing to the beginning of the string. Then inside the loop, we print the character that p is pointing to and move the pointer to the next character. This loop continues until you hit the null terminator. This method is not only syntactically compact but also performs well because it avoids indexing overhead. It's also very intuitive once you are comfortable with pointer basics. Next, let's see how we can rewrite built-in string functions using pointers. Take strlen for instance. Using a simple pointer-based loop, we can calculate the length of a string by initializing a counter and incrementing it each time we move the pointer forward, stopping only when we reach the null character. Here's the code: int my strlen char star str, int len assign 0 while star str plus plus len plus plus return len. Similar logic can be applied to functions like strcpy, which copies one string into another, and strcmp, which compares two strings lexicographically. Implementing these functions yourself is a great way to internalize pointer concepts. Now we move on to an advanced and extremely useful pattern: arrays of string pointers. This is when you have multiple strings, such as the days of the week, and you store them like this: char start days, Sunday, Monday, Tuesday. What you have created here is an array where each element is a pointer to a string literal. This is a highly memory efficient way to store and access collections of strings. You can iterate through the array using a loop, and each pointer gives you access to an entire string. This technique is widely used in real world applications, especially for command menus and argument passing. It's important to be cautious when dealing with string literals. If you write char star str assigned hello and then attempt to change str0 equals to h, your program may crash or behave unpredictably. That's because string literals are usually stored in a read-only memory, and modifying them causes undefined behavior. To safely modify a string, you should use a character array instead. For example, char str equals to hello. This allocates memory to the writable stack segment, allowing safe modifications. Always be cautious of how strings are stored and what kind of memory they occupy. It's now time for some hands-on exercises. Your first task is to implement your own version of three common string functions: strlen, strcpy, and strcmp, using pointer logic only. Avoid array indexing wherever possible. Your second task is to write a program that takes a string and counts the number of vowels, consonants, and spaces in it. Again, use pointers to traverse the string and check character values. These exercises will challenge you to apply what you have learned and help you build muscle memory with pointers. For today's mini project, you will be building a word counter using only pointers. The idea is to traverse a sentence and count the number of words which you can detect by identifying transitions from spaces to non-space characters. This project is more than just a coding exercise. It teaches us how to parse and analyze real-world text data using low-level memory traversal techniques. You will also reinforce your ability to manage pointer-based logic effectively. Here is a sample implementation of the word counter. We use a boolean flag named inward to track whether we are currently inside a word. As the pointer moves through each character in the sentence, we check whether that character is a space or a letter. If we encounter a non-space character and we are not already inside a word, we increment the word count and the set flag. If we hit a space, we reset the flag. This technique is simple, elegant, and demonstrates exactly how text can be parsed at the character level using pointers alone. Let's recap what we have learned today. Strings in C and C++ are arrays of characters ending with a null character, and pointers offer a powerful way to access, traverse, and manipulate them. You have seen how to implement your own versions of common string functions, and you have also completed a practical mini project using only pointers. For homework, challenge yourself further. Implement a strrev function which reverses an entire string using pointers, and go one step beyond by writing a program that reverses each word in a sentence. This task will not only reinforce today's concepts but also prepare you for advanced pointer techniques ahead. Hello and welcome to day 8 of our deep dive into pointers in C and C++. Today we enter one of the most flexible and powerful aspects of function handling: function pointers. These are not just about syntax or indirection. Function pointers allow us to pass functions as arguments, store them in data structures, and create flexible program architectures such as callback systems and command menus. Whether you are building a plugin system or just want cleaner code, understanding function pointers is essential. Let's get started. Before diving in, let's understand what we aim to achieve today. First, we will explore the syntax and concept of function pointers, how to declare and use them. Then we will learn how to pass them as arguments to other functions, unlocking the capability of dynamic behavior. We will also store multiple function pointers in arrays, a foundational technique for menu-driven programs. Finally, we will solidify our understanding through a hands-on mini project, a calculator built entirely using an array of function pointers. By the end of this lesson, you will be able to design flexible systems using function pointers confidently. Let's define what a function pointer is. Unlike regular pointers that store addresses of variables, function pointers store the address of a function. Yes, in C and C++, functions reside in memory too, and we can reference them by their addresses. This allows for something incredible, dynamic invocation of code. Instead of calling a function directly, we can store it in a pointer and call it later, perhaps based on user input or configuration. Here's the syntax: return type followed by an asterisk in parentheses with the pointer name and then the parameter list. At first glance, it might seem complex, but it follows a logical pattern, and we will see that in action shortly. Here's a simple, clear example. We define a function named add that returns the sum of two integers. Then we declare a function pointer funcPTR with the exact signature of the add function. By assigning add to funcPTR, we store the function's address in the pointer. Finally, we call the function through the pointer by writing funcPTR 5,10. This returns 15, just like calling add directly. This demonstrates the function pointers behave like regular function names but provide us the added flexibility to abstract, pass, and switch functions dynamically. Function pointers can also point to functions that return void and take no parameters. In this example, we define a simple greeting function called greet. We declare a function pointer named ptr that matches the void signature. After assigning the function address to ptr, we call it like a normal function. This indirect call executes the greet function. This technique is very useful when you are working with callbacks, for example handling GUI events, timers, or signals where functions are triggered at runtime. Function pointers really shine when passed as arguments to other functions. This is a basics of callback functions. In this example, we define a compare function that returns true if the first number is greater than the second. Now instead of calling it directly, we pass it to another function named process. Inside process, we call the passed in function using the pointer. This is how we delegate behavior. We let a function decide how to operate by supplying the logic externally. This approach creates modular, decoupled code. Let's look at a real-world example, the sort function in C++ STL. This function can accept a comparator, a callback function, as an argument. In our case, we define a comparator named descending that returns true if the first number is greater than the second. We then pass descending to sort. This means the sorting logic is determined at runtime. Want ascending sort? Use a different comparator. Want to sort custom objects? Just provide a custom function. This is powerful and made possible because sort uses function pointers internally. Now let's take function pointers a step further, storing them in arrays. This lets us implement something like a command menu where each option corresponds to a different function. In this example, we define two functions, add and sub, and store them in an array named ops. To execute a function, we use an index like ops0 or ops1. This dynamic lookup is perfect for building interpreters, event dispatchers, and console applications with selectable options. Let's try it ourselves with a basic calculator. We create an array of 4 function pointers, one each for add, subtract, multiply, and divide. Based on an index or user selection, we access the relevant function pointer and execute the operation. This structure is cleaner than a bulky switch statement and easily extendable if you want to add more operations later. This brings us to our mini project, a menu-driven calculator. You will present the user with a numbered menu of operations. Based on the selection, you will invoke the corresponding arithmetic function using a function pointer array. This not only tests your understanding of arrays and pointers, but also introduces you to building flexible, maintainable code bases where logic and control flow are cleanly separated. Here's the core code for the menu calculator. Inside a loop, we display the menu and get the user's choice. If the choice is valid, we accept two numbers as input. Then we simply call the function using operation choice a comma b. Notice how readable and elegant the code becomes. All logic is abstracted into functions, and the menu control structure is compact and intuitive. This is real world level programming using pointers. Now, a few warnings. Function pointers are powerful, but with great power comes great responsibility. First, always ensure that the function pointer matches the signature of the function it points to. Wrong return types or mismatched parameters can cause undefined behavior. Second, never call initialized function pointers. It could crash your program. Third, overloaded functions in C++ can't be directly pointed to unless you disambiguate them, either by casting or using wrappers. Always write clear, well-commented code when working with function pointers. Let's summarize what we have learned. A function pointer is a variable that can store the address of a function, enabling dynamic invocation. Callback functions allow us to pass behaviors into other functions, creating powerful abstractions. Arrays of functions pointers enable scalable, menu-driven programs, and the real-world applications are endless, from sorting and event handling to plugin systems and state machines. Mastering function pointers takes your understanding of C and C++ to the next level. Time for you to build something awesome. Your assignment is to create a scientific calculator. Use CMath function like sine, cosine, and tangent and manage them using an array of function pointers. Design a clear and interactive menu for users to select operations and handle inputs dynamically. This will reinforce everything you have learned today and give you a practical tool you have built from scratch. In our next session, we will level up again by combining pointers with user-defined data structures. You will learn how to create dynamic records, manage them with pointers, and build real-world projects like student databases and contact managers. We are entering the practical application zone now, so stay excited and keep practicing. Hello and welcome to day 9 of our Pointers Mastery course. In today's session, we are diving into an incredibly powerful and practical topic, pointers to structures. You have already learned how pointers can handle primitive types, arrays, and functions. Now you will combine this power with user-defined data types, specifically structures. By mastering this, you will be equipped to build real-world applications such as student databases, contact managers, and inventory systems, where dynamic and efficient handling of complex data is crucial. Before we dive into pointers, let's quickly review that what structures are. Structures allow us to group variables of different data types under a single name. For example, a student structure may contain an integer roll number, a character array for the name, and a float for marks. This mimics real-world data where entities are made up of multiple attributes. To access the members of a structure, we use the dot operator like student.roll. Understanding this is essential before we bring pointers into the picture. Now let's look at how we use pointers with structures. Suppose you have a student variable named S1. To create a pointer to it, you write student.ptr assigned ampersand S1. This gives us access to the structure through a pointer. Instead of accessing members with s1.roll, we can use ptr.roll or equivalently *ptr.roll. Why do we do this? Because when working with functions or dynamic memory, we often don't want to pass around large structures by value. Pointers give us more efficiency and flexibility. Here's where the arrow operator comes in. When using a pointer to a structure, we don't want to constantly write *ptr.roll. That's not only tedious but also error prone. The arrow operator written as like an arrow makes this simple. You can write ptr arrow marks to access the marks field. Think of it as a shortcut, just like using an apartment number to quickly locate a room instead of checking the building plan each time. It keeps your code clean and readable. Now let's understand how pointers help when passing structures to functions. If you pass a structure by value, the entire structure gets copied. This is fine for small data but inefficient for larger records. Passing by pointers like student star s avoids unnecessary copying and allows a function to directly access and even modify the original structure. For instance, a function that updates student marks should use pointers to ensure the changes are applied to the original data and not a copy. Let's take this a step further, allocating structures dynamically. Imagine you are building a system where you don't know how many student records will be created during runtime. In such cases, you can use malloc in C or new in C++ to allocate memory for your structure. For example, student star as assign new student. Once allocated, use as arrow role assign 101 and similar expression to populate it. But don't forget, every new should be paired with a delete and every malloc with a free to avoid memory leaks. Dynamic memory makes your program flexible and scalable. Now it's time to apply what we have learned in this hands-on task. You will dynamically allocate memory for a student, take input from the user and print it. You will use cin and getLine to read values like roll number, name and marks and then display them using cout. This simple program reinforces pointer usage and helps solidify how memory allocation, arrow operator and structure access work together. It's like setting up the building blocks of a larger system. Once you get this part, the rest becomes much easier. Now let's scale up and build a mini project, a contact management system. This project is an excellent way to see pointers to structures in action. Here you will create a contact structure that includes name, phone number and email. Using pointers, you will dynamically manage multiple contacts, adding new ones, displaying them and searching through them. This is exactly how real-world apps like phone books or CRMs manage their data internally. You will begin thinking like a system designer. So what features will this contact manager include? First, the ability to add new contacts. This means dynamically allocating memory for each new record. Second, you will display all saved contacts by iterating through the array or linked list of stuck pointers. Next, searching by name will give you your first taste of implementing logic with dynamic data. And finally, deleting a contact will help you understand memory cleanup and restructuring of dynamic storage. All these operations simulate how professional applications work under the hood. Here's the basic design of our contact structure. It has three fields: name, phone number, and email. Each contact record you create will be based on this design. Using dynamic memory allocation, you will build an array or a linked list of these records. This design is minimal yet practical and scalable. It gives you a strong foundation to add features like sorting, filtering, or saving to files. To take your project to the next level, try adding some enhancements. For instance, implement sorting so contacts appear in alphabetical order, or allow the user to save contacts to a file and retrieve them later using file handling in C or C++. You could also add validation logic to check if the phone number contains only digits or if the email is formatted properly. These enhancements mimic real-world development where software must be robust, user-friendly, and error-tolerant. Let's wrap up with a quick summary. Today we learned how to declare and use pointers to structures and how the arrow operator simplifies memory access. You understood the importance of passing structures by reference to functions and dynamically allocating them in memory. And most importantly, you applied all these ideas to a hands-on mini project simulating a real-world application. This session not only deepened your understanding for pointers but also moved you one step closer to building professional grade software. Your assignment is simple yet powerful. Create a structure to store employee data including their ID, name and salary. Then write functions to create a new employee, display their information and update their salary. All of this must be done using pointers. This exercise will reinforce your understanding of pointer-based structure operations and prepare you for more complex data structures like linked lists and trees coming up next. Hello and welcome to day 10 of our intensive pointers course in C and C++. Today marks the final day of this series and we are going to wrap things up with a deep dive into some of the most advanced, practical and real-world applications of pointers. We will start by looking into generic pointers, memory alignment and pointer-related errors you must avoid. Then we will bring it all together in a hands-on mini project, a dynamic student record system. So let's get started. In this slide, we explore void pointers, also known as generic pointers. A void pointer is a special because it can hold the address of any data type, whether it's an integer, a character, or even a structure. However, the trade-off is that it cannot be dereferenced directly. You must first cast it to the appropriate data type. This makes void pointers very flexible and powerful, especially in cases like dynamic memory allocation and building generic data structures. You will often encounter them in low-level system programming or when building libraries. Let's look at a simple example of how a void pointer works. Here we have a void pointer ptr which is assigned to the address of an integer variable x. Now if we try to dereference ptr directly, the compiler won't allow it. So we cast it to an int star before dereferencing. That gives us proper access to the value stored at that address. Remember that this casting is mandatory, and in C++, pointer arithmetic with void pointers is not allowed. This restriction helps avoid type mismatches and keeps your code type safe. This slide covers some dangerous scenarios involving pointers that you must avoid. First, a wild pointer. A wild pointer is a pointer that has been declared but not initialized. It may point to any random location in memory, making it extremely unsafe. Next is a dangling pointer. This occurs when memory is deallocated but the pointer still points to the old memory location. Any access to such memory can lead to undefined behavior. Lastly, a null pointer is a safe way to say a pointer is pointing to nothing. It helps prevent wild or dangling behavior by explicitly marking the pointer as invalid. Always initialize your pointers and reset them to null after deallocation. Now let's talk about something that isn't obvious at first glance: memory alignment and padding. Processors are optimized to read memory at certain boundaries. For example, reading a 4-byte integer from an address that's divisible by 4 is faster. To make this happen, the compiler automatically inserts padding bytes between structure members. This is known as alignment. So even if you think a structure should take 5 bytes, 1 for a character and 4 for an integer, in reality it may consume 8 bytes due to alignment. You can inspect these effects using the size of operator and control padding using #pragma_pack if necessary. This knowledge becomes crucial when dealing with low-level memory layouts or binary file formats. Working with pointers requires discipline. First, always initialize your pointers. Using uninitialized pointers is a leading cause for segmentation faults. Next, if you allocate memory using malloc, calloc, or new, always ensure you free it using free or delete respectively. Otherwise, you risk memory leaks. In C++, modern best practices recommend using smart pointers such as unique PTR and shared PTR, which automatically manage memory for you. And lastly, avoid doing pointer arithmetic unless it's absolutely necessary. It increases the complexity and error rate of your code. Debugging pointer issues can be challenging, but several tools can make your life easier. Valgrind, for example, is a powerful tool that detects memory leaks and invalid memory access. GDB is the GNU debugger that lets you trace and inspect variables, memory, and pointer values line by line. Address Sanitizer, which is built into many compilers like GCC and CLang, detects out-of-bounds access and use after free bugs in real time. These tools are essential when building complex applications where even a single point error could crash your program. Now it's time to put theory into practice. For your final project, you will build a dynamic student record system using stack pointers and dynamic memory allocation. This is a real-world application where you will use pointers for storing, updating, and managing records. The user will be able to add a new student, delete a student, search for a student by name or roll number, and display all stored records. This project brings together everything you have learned: arrays, structures, dynamic memory, pointer traversal, and menu-driven design. Here's a basic structure you will use to store each student's data. You are defining a student structure with 3 fields: a character array for the name, an integer for the roll number, and a float for the marks. You will allocate memory for an array of these student structures dynamically and use pointer notation to access and manipulate the data. This structure serves as the building block of your records system. To add a new student, you will write a function that uses realloc to increase the size of the dynamic array. Realloc takes care of allocating a larger memory block and copying existing data to it. Once the new block is allocated, you prompt the user for the student's name, roll number, and marks, and store this information in the last index of the array. This approach allows the number of records to grow as needed without setting a fixed size in advance. Your application will be menu driven, which means the user will be presented with options in a loop. They can choose to add a student, delete one, search for a specific record, or display all students. This kind of program not only tests your pointer skills but also your ability to build modular, user friendly applications. All of these operations will involve pointer manipulation, such as navigating arrays of structures, checking for null pointers, and reallocating memory. Here's an example of how the program will behave. The user inputs data for a student, let's say John, roll number 101, with marks of 88.5. The system then confirms that the student has been added. After that, it loops back and displays the main menu again. This feedback loop is essential in user-driven programs and gives a clear interactive experience. To push your skills even further, here's a challenge for you. Enhance your project by saving student records to a file so they persist between program runs. Add GPA calculation by storing marks across multiple subjects and computing averages. For this, you will need to use 2D dynamic arrays or pointer-to-pointer concepts. These extensions will make your program more robust and realistic and prepare you for advanced software engineering tasks. Let's recap what we have covered today. You have learned about void pointers, the proper way to use them. You now understand the dangers of wild, dangling, and null pointers and how to avoid them. You got an introduction to memory alignment and padding and learned how to use tools for debugging pointer related issues. Finally, you applied all of this in a practical project that simulates a real world record management system. This was the accumulation of your 10-day journey with pointers. Congratulations, you have completed this 10-day course on pointers. You have gone from the basics of pointer declaration to advanced usage like dynamic memory and function pointers. More importantly, you have built confidence in using pointers safely and efficiently. From here, you can dive into more advanced topics like data structures, memory management, and systems programming. Keep building, keep experimenting, and continue your journey into becoming a world-class developer.